12. What about 9? Bigger than 8? Do we have space? Yes. 9 and 12. 6. Bigger than 5, less than 8. 6. Do we have space? Yes. So this is a 6, 7. This is a final out. How many level? 2 level. So for example, when you access the data 1, how many IO do you need? Data 1.
3.
1, 2, 3. What about the 9?
3.
1, 2, 3. What about 5?
2.
1, 2. Which means maximum
3.
3. Okay? Maximum 3. It has the maximum bound, upper bound. So it's much better than search tree. It's the balanced. We have a question. What if 13 is inserted? Why don't you try? 13 is inserted. Same algorithm. Why don't you try? 13.
We'll have one in the level, third level.
So that's the key point. So let's try together because it's almost a time's up. So 13 is inserted. We need to find the proper position. Okay, from the top. So 13 is bigger than 8. So 13 is supposed to be here, right? But it is the full. So full, in case of full, 9, 12, 13. Split. So 9, 12, 13. This one is midway, right? There might be no problem. Then 12 should be promoted. Promote here. Is there any space? No. It is split. It's so in case of full. It's the same thing. It's kind of recursive. Yeah. Then 12 will be inserted, but it's a full 5, 8, 12. Which one is the middle value? 8. So we can split. Exactly same node structure. Less than middle value 5. Bigger than middle value 12. Okay? Then 8 will be promoted. There is no paradox we can create. Then this one will be 8. Get it? It's the same thing. We can apply always the district algorithm. That's not done yet. We need to rebuild all the children. Always check the children from the top, less than 8. Bigger than 8 goes to here. Less than 5 goes to here. Bigger than 5, less than 8. That is this one. Bigger than 8, less than 12 goes to here. And bigger than 12 goes to here. Oh, not this one. So this. Okay. How many levels? 3 levels. Okay. We can keep the same level balanced tree. So when we access the 13, how many are you?
4.
1, 2, 3. When we access the 12,
3.
3. When you access the 8,
2.
okay. So this is the B3 index. Problem. In case P is equal to 4, okay, then it will be like this. 1, 2, 3. So when 4 is inserted, what will be the middle value? 2.5.
2.
So in our case, in this classroom, we will select this one as the middle value. Cardinal half and the left-hand side. Most the right-hand side of the left-hand side, the block. Depending on the DBMS, some of them select this. Sometimes they make the average, okay? But that's additional cost. So, but in our class, we will select this one. So which means if we split this, it will be 1, okay? And 3, 4, and 2 will be promoted. Okay? So this is our rule. Sometimes the 3 can be selected as the middle value. But it's not a problem as long as consistent. Okay? So in our class, even the exam, we will select this one as the middle value. So that is one. It's a minor problem, not big problem. Any issues in this, the B3 index, can you find in terms of balance? For example, when we travel to the Manhattan from Bridgeport, so some of the train, 1.5 hours. Some of the train, 60 minutes. It's an upper bound, it's mostly 1.5 hours. But some of them are fast, it's bypass a lot of the train station. So, instead, what about the helicopter? Chopper. Chopper always 1 hour to the Manhattan. No matter what happens, which one will be better in terms of the performance? Helicopter is better, okay? Even it takes 1 and 35 minutes. It's longer than that, but it's always fixed time. So in terms of computer system, which one will be better to decide something? Fixed, guaranteed time is more important. Computer system. So, but in this case, sometimes 2, sometimes 3, sometimes 4. It has, even though upper bound is not fully balanced. Okay? So B3 is balanced overall, but for each, it's not fully balanced yet. Okay? So, to address that one, we can make fully balanced, that is B plus 3. Idea. How can we make the fully balanced? Any idea? Because of this one, right? They are in the middle. Can we, if we can move down to the leaf node, terminal node, it will be fully balanced. Another benefit of such a fully balanced is, for example, in this case, I'd like to linear search in order. 1, 3, 5, 6, 7, 8, 9, 12, 13, which means you need to up and down. Okay, backtracking. You need to do the backtracking a lot to sequential reading. However, if we have all the data in the leaf node, we can read sequentially. We don't have to up and down. We can reduce a lot of I/O. So, B plus 3, we can move down all of this problem. How can we do that? So next class we will talk about how to make it the B plus 3 to, actually not, it's a different approach, similar but different. So we will see how to make the B plus 3, then continue further the normalization. Okay.